Hello everybody, I'm Risset and I will be presenting the paper entitled Faust2Fpga for ultra-low latency, preliminary work in the Syfala project. So there is a number of authors here, and basically this work is a collaboration between the Gram Institute and the City Laboratory in Lyon. We are presenting actually preliminary work in the sense that we started this project 2 years ago. Try to build a compiler from Faust2Fpga, and it happens to be a little bit more complicated than we thought. So we are mainly presenting the project and very preliminary results. So let's start about a little bit of context of this collaboration between Gram and City. So the initial motivation of this work popped up during the discussion that we have between the City and Gram. We were having some skills in high-level synthesis and compilation at City, and of course you know the wonderful work of Gram on FAUST and the FAUST library. So we tried to basically generate directly FPGA bitstring directly from FAUST program using the FAUST compiler. So the first project was founded by the Fédération Informatique de Lyon, the FIL, and it was a small project, and it happened to be a little bit more difficult than we thought. So we wrote a second project, which is a bigger project, and it has been accepted in September. It's an ANR project, and we'll be collaborating with the LMFA in Lyon. And we hope that this Faust2Fpga compiler will finally emerge during this project. And I would like to take this opportunity to talk about the Emerald team, which is an official research team that we are trying to launch, which is a collaboration between the City and Gram, and it would be an association between inside Lyon, Gram, and we hope INRIA also. And the team will be called Emerald for Embedded Programmable Audio System. But this is not started yet. We are thinking about it, and we hope that it will succeed. So our motivation for this compiler was to provide very low latency for audio processing. So this is not new. Some work have been using FPGA for audio processing, either for high performance or for low latency, but none of this work have really provide a compiler. So our idea was to use 3 important technologies. First, of course, the FAUST compilation suite. Then the optimization of fixed point arithmetic, and finally the high-level synthesis, which is a technology that have been studied for a while, but which is now coming at a state where it can be used by many people to bridge the gap between high-level and hardware. So the prototype I will be presenting is this one. We start from a FAUST program. We generate C++ with the FAUST compiler, which is tuned for this process, of course. We then generate VHDL with HLS compiler, and then with the synthesis we generate a bitstream for the FPGA. We use the Zibo board, which contains an audio chip for our experimentation, but of course we can target other boards. So let me start with the technical presentation of the project, and first I would like to precise what we call ultra-low latency. So for us it means a latency between 50 microseconds and 500 microseconds, which is at standard sample frequency between 1 and 25 sample latency. And we want to use that for musical instruments, but also active acoustic control, and there are a bunch of industrial application, for instance, in the vibration control domain. So could we use powerful CPUs for that? But not really, because these powerful CPU usually have also a problem with memory latency, and to hide this memory latency they have to group samples in buffers, which goes from the cache to the memory, and if you have a 256 sample, then it means 256 sample latency. So what kind of processor is an FPGA? So an FPGA is basically a grid of configurable cells. Each cell is a very small logic function of 4 input, and it also contains a very small register of 1 bit. So an FPGA is basically network of these simple cells interconnected with a grid which can be configured. And programming an FPGA is actually configuring this grid and these logic cells so as to implement a particular hardware function. So this is basically the principle of FPGA. So in practice, there are other components on FPGAs. So one thing important is that we have a small multiplier, which are hard-coded, which are not logic cells. And we also have small memories, which are called block RAM. And more important, in recent FPGA, we also have what is called the processing system, which is a real core, where, for instance, an ARM core with peripheral and memory controller and connected to a memory and so on, which is not directly on the FPGA, but which is on the same chip. And so to give you an idea of the number, for instance, on the Zinc FPGA that we use on the Zibo, we have 2 ARM processor core running at 1 gigahertz. We have 28,000 logic cell, 80 DSP blocks, the multipliers, and 60 block RAM. But you see that the size of the block RAMs are quite small. And last thing, the FPGA is not running very fast. It's usually running between 100 and 200 megahertz. So now that we have this FPGA and that we can interface it with an audio chip, what does it mean to compile a FAUST program on it? But of course, it means that when we have a FAUST program, we will probably generate a FAUST IP for intellectual property, which is a FAUST circuit that corresponds to the program. But more precisely, what we would like to do is to have on this IP only the computing part, the DSP computing part of the FAUST program. And the controllers would be implemented on the ARM core, because the controller don't need this very low latency, and we have limited resource on the FPGA, and we would like to use them only for what is really low latency. There are a number of technical problems, and I will try to give an overview of them. The first one, of course, is that programming an FPGA is hard, and it takes a lot of time, and for that we will be using HLS. I will explain how. The second one is that we also have to do some VHDL program by hand. For instance, if you want to interface the audio chips, and if we for that we need the embedded programming skills. But more important are the program that some FAUST programs are using a lot of memory for echoes, and we don't have that much memory on the FPGA, so we will have to use the external memory. I will mention this problem. We also have some programs that we have performance problem, but there again we will use HLS for that. And the last thing is that on, as I mentioned before, we will be using some part of in hardware and some part in software. So as some of you might know, it's a hardware software problem, and it's basically much more complicated than hardware or software. So let me talk here about how HLS can help us in mapping FAUST program to FPGA. So here we have a simple loop, a number of filters. We have NBIN mode filters, which are basically can be executed in parallel. But if we write that in C, basically this semantic is sequential, but we know that we can execute that in parallel, so we can simply add a pragma to unroll the loop, the body of the loop, and the HLS tool will know that when the loop is unrolled, it can try to parallelize it, and it will realize that this, for instance, 8 instruction can be executed in parallel, and it will of course gain execution time. And this pragma here is another important optimization. It allows to overlap several successive loops. And with these two pragma, we have also almost the most important optimization in parallelization that can be used, but there are also some other. This pragma here is to help us indicate the HLS tool that this array filters will be stored on the block RAM and spread over the block RAM, even if it's a big array. So as you see, the HLS tools provide us with help with very simple modification of the basic, I would say, C++ code generated by FAUST to a program that can be mapped on the FPGA. Now, the second problem is the access to the memory. So let's say that our FPGA clock is at 8 nanoseconds. It meets 120 megahertz. So it's approximately 2,500 cycles per audio sample. So if we use block RAM for storing the sample, block RAM can be accessed quite quickly within one cycle, but they have a limited size, as we saw. If we use external memory, well, we have a lot of room for our sample, but it's slow. It's between 100 cycle and 200 cycle. So we have to make a choice. So if we are to use the external memory and go through the ARM, because we need a lot of memory, then we have to sacrifice some latency. And basically, we have to rethink the classical optimization rule of FAUST program. For instance, an oscillator will not always be implemented with waveform and editable constructor because it's a lot of memory accesses. Maybe we can use a filter to generate an oscillator. So basically, we have to face this memory well problem, and there are many solutions for that problem. Either we can, as I said, use computation rather than storing samples. We can use pipelining between successive instances of FAUST computation. We can use caches. Again, we trade latency against performance. All these solutions have to be evaluated, and of course there are some other FAUST programs that do not have this problem because they don't use that much memory. So now I will talk a little bit about arithmetics, because when we target FPGA, we need to use fixed point arithmetic. So for that, I will use the example of the FAUST Bell model program, which has been published before, and which is an example of physical modeling for emulating a bell. This program is basically a set of parallel B quads which are then added together. And if you look at one filter, it has a particular structure, and this blue number here are the size of the integers that goes on each wires. So forget about floating points. Imagine that we are computing using fixed point integer, and this m is the size of the integer before the comma, and this size is after the comma. So the idea of fixed point arithmetic is that we can optimize these sizes, and we have this skill in CityLab about technologies to have the best size for a given precision at the output of the computation. So let me give you some results. So these are some HLS results, so high-level synthesis results from Vivado, running on the Bell model with 50 mod, and it gives you the number of block RAM, number of DSP, and the number of logic cell used on the FPGA. So as you can see that it's floating with floating point. We use about 10% of the block RAM, and we have more lookup table than we had. So this implementation does not work because we use more LUT than the FPGA contains. So now if we run the same implementation with fixed point operator on 32 bits, then you see that the number are quite similar to the floating point implementation, but again, we cannot map this program on the FPGA. So now if we use the fixed point operation with 16 bits, and we have proved that these 16 bits are sufficient to have the same precision that the other implementation, then you see here that the use of the resource of the FPGA are correct. So we gain a factor 2 approximately between 32 bits and 16 bits. So you see that it's a very important optimization to have this bit width of the integer carefully taken care of. So these arithmetic optimization can be done with a tool that we have developed at INSA, which is called Flopoco. Flopoco is a tool developed by Florent de Dinechin, and basically we have many possibilities from going from a FAUST program to the FPGA IP. Either we use a direct path that I showed you before, or we add the FAUST compiler with a bit width analysis and we generate fixed points in C++, or we do the same thing and we generate directly the SGL if we are not happy with the HLS tools. So let me show now some result about the performance that we get with this first prototype compiler, so very prototype again. So as I said, we start from a FAUST program, we generate an IP in VHDL with HLS, and then we map with these I2C and I2S interconnects the FAUST IP onto the FPGA, and we hear the sound once it's loaded on the board. So the whole process takes about 10 minutes, and the choice that we made for this first Syfala version is that we use Xilinx tools, of course, as I said, and it means Vivado and Vivado HLS. We have implemented a new option in the FAUST compiler, which is called -OS for one sample, and the C++ generated with that option is doing computation only on one sample. So actually, the FAUST IP implement the computation on only one sample. So this was our solution to this very slow latency. We have floating point operator now. We have not implemented the fixed point operator yet. We have two streams, I mean stereo, for input and output. And we have not implemented the controller. We only implement the computing part of the DSP. So we have two versions. Either the memory is stored in block RAM or it uses the external memory, but we have latency issues for this second version. So let me show how it works in practice. We have a command line interface using makefiles, and if you run sorry, the compilation, the make command with the Carpus strong program that I will show you, well, you first have the FAUST command that compiles the DSP program onto C++ program. Then you use the Vivado HLS command to run the high-level synthesis, which is about 32 seconds. It's really fast. Then you create the Vivado project, and then you execute the synthesis in Vivado, and this is what takes maybe all the time. It's about 10 minutes to compile this very simple program. However, it's not very long. I mean, as soon as you target FPGA, you have long compilation time. So now about the latency. So this is a very simple Carpus strong program that I have in line because I want to know exactly what's going on the program. So we have slider here, but they are not implemented. We only use the default value. And you can see that the use of the different resources is quite small, but that was not really the test that we wanted to have here. We wanted to know about the latency. So the latency that we have between one sample in input and one sample at output is about 840 microseconds, which is quite more than what we wanted. But we realized that this latency was coming from the ADC chip, and the ADC chips has a 800 microseconds latency by default. So it's not all the chips do not have this latency. We have to use another chip which has a smaller latency. And concerning the FAUST IP, it has simply one sample latency, which is 20 microseconds. And we think that we will be able to have this latency for many FAUST programs because, well, but we have not time. We did not have time to test more than that yet. Okay, so that's it. As you see, we have a lot of work to do. The most important to my opinion, is that we have to separate hardware and software and implement the controller on the ARM CPU. And then we have to optimize the latency access for the sample. So these are the two tasks that will really make this compiler very efficient. Of course, we have to implement the fixed point on the backend of FAUST compiler, but this will be useful for other people too. And we are quite confident about that because we have been starting working on that, and it's a very interesting topic. Now, we also think that we have to target other kind of platforms, so larger FPGA, because of course the ZIBO is a very small prototyping board, and low latency ADC chip, as I said before. And we fortunately we have a funding for that, and this will be done in the FAST project, which will be started in March next year. I mean. Okay, thank you for your attention.